Let us continue molecular orbital theory. In the molecular orbital theory, we are taking oxygen. Oxygen number of electrons 16. Therefore, electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px, pi 2px2 is equal to pi 2py2 into pi star 2px is equal to pi star 2py. Now, O2 molecule is having 16 electrons. In that 16 electrons, 14 electrons are filled. The remaining 2 electrons are there. That 2 electrons we have to fill as per Hund's rule. As per Hund's rule in the sense here 1 electron, here 1 electron. Here 2 unpaired electrons are there. Therefore, it is paramagnetic. 2 unpaired electrons. Therefore, we can say it is paramagnetic. Then we will say bond order. Bond order, how much you will say? Here sigma 1s. Sigma 1s cancels with the sigma star 1s. Sigma 2s cancels with the sigma star 2s. Then this sigma 2pz will form one sigma bond. This sigma 2pz2 will form one sigma bond. Therefore, between O2, one sigma bond will be there. Sigma bond will be there. This pi 2px2 is there. Here pi star 2px is there. This one electron will cancel one electron here. So remaining one electron is there. That electron forms half pi bond. Then pi 2py2. Here pi star 2py1. This pi star 2py one electron cancels one electron here. So remaining one electron is there. That forms half bond. So here half pi bond. It is half pi bond. Therefore completely one pi bond. One pi bond is formed. Therefore bond order is 2. Okay, therefore in the oxygen molecule double bond is there. On in the double bond one is sigma, one is pi, we can say. Next we will take a O2 plus. We will take O2 plus. In the O2 plus in the sense here O2 contains 16 electrons. O2 plus in the sense 15 electrons. One electron we have to remove. If from this one electron you remove it, that means this pi star 2py is there. No, this electron remove it. Therefore, what you will get? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, then pi 2px2, pi 2px2, pi 2py2, pi 2py2, then pi star 2px1, pi star 2px1 is equal to pi star 2py 0. This is 0. Here no electrons. In this pi star 2py no electrons is there. Pi star 2px contains one electron, we can say. Sir. Now, here one unpaired electron is there, therefore it is paramagnetic. One unpaired electron is there, therefore we can say it is paramagnetic. Here, magnitude of paramagnetic nature. This magnitude is low, we can say. Here, the magnitude is high, we can say. Magnitude is high, we can say. Here, paramagnetic nature, magnitude is more because of two unpaired electrons. Here, paramagnetic nature, magnitude is less because of one unpaired electron. Now, we can see the bond order. Bond order is how much you will see. Now, bond order in the sense sigma 1s, sigma star 1s cancel, sigma 2s, sigma star 2s cancel, sigma 2pz. Sigma 2pz will form one sigma bond. Okay. Then this pi 2px 2. Here pi star 2px1. This pi star 2px, this electron cancel this electron. So remaining one electron is there. That electron makes half pi bond. This pi 2py2, this is forming one pi bond. Therefore, 1.5 pi bond is formed. 1.5 pi bond. Therefore, totally how much means 2.5 is the bond order. So, what is the bond order in O2 plus? In O2 plus, what is the bond order means 2.5 we can say. So, next we will take a what in the sense O2 minus we will take O2 minus 1 that will take O2 minus is called superoxide. This O2 minus is called what in the sense superoxide. O2 minus in the sense to this one electron we have to add to O2 one electron add it, you will get O2 minus. Then what is the electronic configuration? We will see sigma 1s, sigma star 1s2, sigma 2s2, sigma star 2s2, then sigma 2pz2, sigma 2pz2, then pi 2px2, then pi 2py2, pi 2py2, then we can say pi star 2px2, pi star 2px2 equal to pi star 2py1. Okay, so we are adding one electron into this oxygen, we are getting O2 minus. Okay, this O2 minus contains one unpaired electron, therefore it is paramagnetic. It is what in the sense paramagnetic we can say. Now here magnitude of paramagnetism and here magnitude of paramagnetism remains same, because here one unpaired electron, here also one unpaired electron is there. Then we'll see the bond order here. What is the bond order that we will see? Now sigma 1s, sigma star 1s cancel, sigma 2s, sigma star 2s cancel, then sigma 2pz. This sigma 2pz forms one sigma 1. Okay, one sigma 1. This pi 2px2, pi star 2px2 cancel each other. Pi 2py1, this is one electron, cancels pi 2py one electron, remaining one electron is there, that one electron forms half pi bond. Okay, half pi bond. Therefore what is the bond order in the sense? 1.5. 1.5 is the bond order here. Okay, sir. In O2 minus 1.5 is the bond order. This O2 minus is explained as per molecular orbital theory. This O2 minus is explained by valence bond theory. In what way? That we will see. Okay, O2 minus explained by valence bond theory. This O2 minus is called superoxide. This O2 minus is called superoxide. How valence bond theory explaining this structure we will see. In this O2 minus 2 oxygens are there. Oxygen comes under group number 6. Group number 6 in the sense its valence shell contains 6 electrons. This valence shell also contains 6 electrons. Now, minus charge we have to give to any one of the oxygen. Therefore, another electron we will write. Now, here one bond we have written. Okay, one bond we have written. Next resonance structure we will see. It is one of the resonance structures. Next resonance structure we will see. For this oxygen, we will write 6 electrons. 6 electrons. For this oxygen, we will write 6 electrons. Then this minus charge we will give to this left side oxygen, and another electron we will write here, and bond we will give here. Okay, these two are resonance structures. So what is a resonance hybrid? That we will see. Now resonance hybrid, how it will be there, that point we have to see. Okay, two oxygen atoms in a linear, so two oxygen atoms in a linear. Each oxygen is having how many lone electrons? In the sense 5 lone electrons. Each oxygen is having 5 lone electrons. Each oxygen is having 5 lone electrons. Okay, minus 1 is there, for a minus 1 is there. Okay, now this right side oxygen is having one extra lone electron, left side oxygen is having one extra lone electron. Okay, that extra lone electron we will write at center of both. That extra lone electron we have written at center of both. Okay, next we will write this oxygen contributing one electron for bonding, this oxygen also contributing one electron for bonding. So each oxygen contributing one electron for bonding, that we have written. Next, what we will do here in the sense, now we will make these 3 electrons to form a bond. Okay, understand that 3 electrons made a bond, therefore it is called 3 electron bond. This bond contains 3 electrons, therefore odd number, therefore we can call this is as odd electron bond, we can say. Then minus 1 is there in the right side, here minus 1 is there in the left side. Now distribute minus equally to both oxygen, therefore minus 1 by 2, minus 1 by 2. It is called superoxide. This superoxide ion O2 minus is this one. Okay, valence bond theory says that this O2 minus, this superoxide contains odd electron bond, therefore it is paramagnetic. It is said by valence bond theory. How this molecular orbital theory says? Molecular orbital theory says that the superoxide ion is having one unpaired electron, therefore it is paramagnetic. Therefore, molecular orbital theory gives a clear idea about paramagnetism of superoxide than valence bond theory. Okay. Next, we will take O2 2 minus. We will take O2 2 minus in the sense to this superoxide you add one electron, you will get O2 2 minus. Now that electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then sigma 2pz2, then pi 2px2 equal to pi 2py2, pi 2py2 into pi star 2px2 equal to pi star 2py2, pi star 2py2. Okay, this is O2 2 minus. The configuration we have given here, unpaired electrons are not present, therefore it is a diamagnetic. Diamagnetic, you can say. What is the bond order in this one? That we will see. We have to go for bond order. Now we can say sigma 1s, sigma star 1s cancel, sigma 2s, sigma star 2s cancel. The sigma 2pz gives one sigma bond. The sigma 2pz gives one sigma bond. pi to px and pi star to px cancel, pi to py and pi star to py cancel. Therefore, only one sigma bond is there. Therefore, what is a bond order means bond order is 1, we can say. Now, this O2 2 minus, this regarding this peroxide, we will give this O2 2 minus peroxide structure will give peroxide structure. This oxygen will write. This oxygen group number is 6a. Therefore, this valency shell is having 6 electrons. This valency shell is having 6 electrons. This oxygen group number also 6a. Therefore, this valency shell is having 6 electrons. Okay, minus 2 will split as a here minus 1, here minus 1 will split. Therefore, additional 1 electron we will write. Additional 1 electron we have written. Then between these two electrons, we will write a bond. Between these two electrons, we have written a bond. This is called a peroxide, we can say. This is called peroxide as per valency bond theory. Okay. Now we have given a bond order for all. Now we will give a bond length order. Bond length order we will give. Okay. Bond length order we will give. So if bond order is high, if bond order is high, bond length will be low. Okay. So bond order is high for which one in the sense O2 plus. So bond length is O2 plus. For O2 plus, bond length is less. Next, smaller bond order is this O2. Therefore, bond length is higher. Next, smaller bond order is O2 minus. That will write. Next one is this O2 2 minus. It is the order of what in the sense bond length. So bond length is highest for which one in the sense peroxide, and least for which one in the sense O2 plus. Okay. Next we will take what molecule in the sense F2 molecule we will take. Next we are taking what molecule in the sense F2 molecule we will take. F2 molecule in the sense it contains 2 fluorine atoms. Fluorine atomic number is 9. Therefore, total number of electrons is 18. 18 in the sense like this. O2 2 minus is having 18 electrons. Therefore, this is the configuration. This is the molecular orbital configuration for F2. Therefore, what is the bond order means 1. What is the unpaired electrons means 0. Therefore, diamagnetic. This is for F2. Next, we will see about Ne2. We will see Ne2. Ne2 in the sense 20 electrons will be there. That 20 electrons will write sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then sigma 2pz2, sigma 2pz2, then pi 2px2 equal to pi 2py2. Then we will write pi star 2px2, pi star 2px2 equal to pi star 2py2, pi star 2py2, then sigma star 2pz2. Sigma star 2pz2. Here if you see, all the bonding electrons will be cancelled by anti-bonding electrons. Therefore, what is a bond order means 0. Bond order is 0 means no bond. No bond in the sense this molecule do not exist. Okay, this molecule is does not existing. This molecule does not existing. That's why we will say noble gases exist in monoatomic molecules. Noble gases are monoatomic molecules, but not diatomic molecules, we will say. Okay. So this is about molecular orbital electronic configuration for homodiatomic molecules, we can say. So next we will see about linear combination of atomic orbitals. We'll see linear combination of atomic orbitals means SS combination gives what in the sense sigma S and sigma star S. SS combination. PP combination gives what in the sense sigma to sigma P, sigma star P. Then pi P and pi star P. Okay, PP combination gives like this. Now we will see about SP combination. Now see, we will see about SP combination. That means SP combination means what is possible. Sigma is possible or pi is possible. That we will see. S orbital comes in the sense only sigma is possible. S orbitals never form pi bond. S orbitals never form pi bond. Therefore, SP combination means only sigma is possible. Pi possibility never. Okay. Now we will take one S orbital. So we are taking one S orbital. We will take at center. We will write the nucleus. Then sign of psi is suppose positive we will give. Okay, we can give either positive or negative because it is symmetric. Okay, next we will take p orbital. P orbital is a dumbbell, we will say. In the p orbital at center we will say write the nucleus will write. For one lobe you will give one sign, for another lobe you give the opposite sign. Now it is going for linear combination. Linear combination in the sense two possibilities are there. One is what in the sense addition overlap, another one is what in the sense subtraction overlap. Another one is subtraction overlap. Okay. Now addition overlap we'll see. Now this is a s orbital. S orbital we have drawn. For s orbital we will give the nucleus. Then p orbital one lobe is overlapping with the s orbital one end. Okay, p orbital we have given. For this also we have given nucleus. Next we have to give charges. We have to give charges in the sense for s orbital. Suppose you are giving positive sign. Then for p orbital, the lobe which is overlapping with s orbital should be given positive. Then only addition. Same sign should be there. Then opposite sign you give here. Okay, this is a addition overlap. This addition overlap in the sense constructive interference here construction takes place. Okay, so this addition overlap, this sp combination gives molecular orbital. That molecular orbital, how it is there in the sense that molecular orbital will be like this is there. Okay, it is a molecular orbital. Okay, now it is a nucleus of, it is one nucleus, it is another nucleus. Okay, this is what in the sense sigma sp we can say. Why sigma? In the sense overlapping takes place along the internuclear axis, therefore sigma. So we said it is sigma sp we said. Next we will go for subtraction overlap. In this subtraction overlap we will take s orbital we have taken. Then we will write p orbital. We will take p orbital one lobe is overlapping with the s orbital of one end. Okay, so we have given sp overlap we have given. Here we will give nucleus. For this we will give nucleus. For this we will give nucleus. Then sign of psi we will give. Sign of psi here, if we give positive, the lobe of p orbital which is overlapping with s orbital should be given opposite sign. Then only subtraction overlap. Then here negative means here positive you give. Here subtraction overlap in the sense here destruction takes place. Due to destruction, how it will be there we'll see. It is one nucleus, it is another nucleus. Now this s orbital is going left side completely. Okay, right side nothing is there. So this p orbital what happens means left side small lobe, right side big lobe, like this will be there for p orbital. Here what is that means a nodal plane. Here what means a nodal plane? That means electron cloud is not there here, therefore it is antibonding. Therefore we can say sigma star sp. Therefore sp combination gives what in the sense sigma sp and sigma star sp we can say. Okay, next dd combination will give. dd combination, dd combination in the sense here also addition overlap and subtraction overlap possible. dd combination gives what bonding molecular orbital means delta. This delta bonding molecular orbital and delta star bond anti-bonding molecular orbital, like this we have to say. Okay, so delta molecular orbital, delta star molecular orbital will be obtained by dd combination said. Okay, next we'll discuss about molecular orbital electronic configuration for a heterodiatomic species. Heterodiatomic species we will see. Now we will take which one in the sense nitric oxide we will take. Now we have taken a nitric oxide. Here nitric oxide in the sense here what are the two atoms present means nitrogen and oxygen. Now in the nitrogen atomic orbitals and oxygen atomic orbitals undergo linear combination and giving molecular orbitals. Sir, what is the order of energy of molecular orbitals? That we will see. Order of energy of molecular orbitals we will see. Here least energy molecular orbital is sigma 1s. Then next one is sigma star 1s. Next one is sigma 2s. Next one is sigma star 2s. Okay. After that, what will come in the sense sigma 2pz. That means in the nitric oxide, the molecular orbital energy level is as like oxygen, as like oxygen. Okay, then but energy will be different with the oxygen. Then pi to px is equal to pi star to px, pi star to px. Then pi star to px not here mistake is there. It is pi to py. It is pi to py. Next we will say pi star to px is equal to pi star to py, pi star to py. Next what will be there means sigma star to pz will be there. Now let us fill the electrons here. Here we will fill the electrons. Nitrogen contains 7 electrons, oxygen contains 8 electrons, 8 plus 7, 15. That 15 electrons will distribute to 4, 6, 8, 10, 12, 14, then 50. Okay, now one electron, one unpaired electron is present, therefore it is paramagnetic we can say. Now what is the bond order? What is the bond order? We will say sigma 1s, sigma star 1s cancel, sigma 2s, sigma star 2s cancel. This sigma 2pz gives one sigma bond. Okay, this sigma 2pz gives one sigma bond we can say. Next we will see about this pi 2px. If this one electron, pi star 2px, one electron get cancelled. So remaining one electron after pi 2px gives half pi bond we can say. Then this pi to py gives 1 pi bond, therefore 1.5 bond is present, therefore what is the bond order means 2.5 is the bond order. Okay, next we will go for no plus. No plus, okay, nitrosonium ion. No plus name is what in the sense nitrosonium ion we can say. Okay, for this nitrosonium ion, what is the configuration in the sense here in this NO you remove one electron, that means pi star 2px you remove it, then we will get a nitrosonium ion. So sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, then pi star 2px1, pi star 2px2, pi star 2py2, pi star 2py2. This pi star 2px, this electron you don't write it, pi star 2px electron we need not write, it is nitrosonium ion. Now what is the bond order in the sense 2.5 plus 0.5. Why? Because this pi star here pi star will not be there, here one mistake is that this star will not be there. Okay, now this pi star 2px electron we have removed, therefore bond order will be raised by half. Therefore what is the bond order in the sense here 3, here bond order is 3, here bond order is 2.5. Sir, okay, so nitric oxide and nitrosonium ion, how the bond order is there we know that. Now what is the bond length? That bond length we will see, higher the bond length sorry, higher the bond order, lesser the bond length. So bond order is high, so NO plus is having less bond length when compared to NO. Okay, so NO plus NO bond length we have given. NO plus is having bond order high, therefore lesser bond length. Okay, next we will take what in the sense carbon monoxide we will take. Okay, now we will take carbon monoxide. In the previous case what we have taken means nitric oxide we have taken, now we have taken carbon monoxide. So carbon monoxide electronic configuration will see. Now carbon is sigma 1, here least energy orbital is sigma 1s, next one is sigma star 1s, next is sigma 2s, next one is sigma star 2s, next one is what in the sense here sigma 2pz shall we give, or pi 2px shall we give in the sense as like carbon, therefore we will give a pi 2px we will give equal to pi 2py, then sigma 2pz, like this we have given. Okay, sigma 2pz. In the previous case like this, like oxygen we have given, now like carbon we are giving, therefore sigma 2pz we have written after pi 2px. Sir, okay, now we will give the electrons, we will give, sorry, okay, we will give electrons. Carbon is having 6 electrons, oxygen is having 8 electrons, totally 14 is there, therefore 2 4 6 8 10 12 14, 14 electrons is over, therefore what is the bond order we are expecting in the sense bond order is equal to 3. It is just like nitrogen, therefore bond order is equal to 3 we said. Okay, next we will see CO plus. Okay, we have taken CO plus, we have taken, for CO plus what we will do in the sense CO plus in the sense we have to remove one electron from sigma 2pz, therefore one electron is going away in the sense bond order is decreased by half. Why? Because we are removing one electron from bonding molecular orbital, therefore bond order decreases by half, therefore bond order is equal to how much in the sense 2.5. Now we will see the bond length. Bond length is how much in the sense for CO less than CO plus. Okay, CO less than CO plus. Why CO is having less value means bond order is high. Okay, so now we will see experimental result, what experiment says. Okay, so what experiment says regarding this bond length, that we will see. Regarding experiment in the sense CO bond length, CO bond length as per experiment is how much in the sense 1.128 angstrom, 1.128 angstrom. CO plus, CO plus how much in the sense 1.115 angstrom, 1.115 angstrom. Okay, it is experimental result. So experimental result says that CO is having higher bond length, CO plus is having lesser bond length. That is this experimental result is against, is opposite to our expectation. Therefore here what it says, what experiment says, as per experiment which is having higher bond length in the sense CO is having higher bond length, CO plus is having lesser bond length. Okay, as per experiment bond length of CO plus is less, therefore bond order, if you see bond order how it is, how should be there means CO plus should be greater than CO. Okay, so as per experimental result bond length of CO plus is less, therefore CO plus should have higher bond order. So CO plus should have higher bond order means When it is possible means if you remove one electron in this CO from anti-bonding molecular orbital, then CO plus will have higher bond order. Okay, so as per experiment, CO plus should have higher bond order. So CO plus will have higher bond order when if you remove one electron from anti-bonding molecular orbital of CO. Okay, so now to have higher bond order, to have higher bond order for CO plus remove remove an electron remove an electron from anti-bonding molecular orbital of CO. Okay, if you do like this, then only experimental result can be explained. So we have to remove from where we have to remove the electron from CO, anti-bonding molecular orbital. Sir, so in CO we have to remove electron from anti-bonding molecular orbital. So anti-bonding molecular orbital means what is the possibility? Only sigma star 2s is the possibility. Therefore, from sigma star 2s electron is removed in the sense sigma star 2s should have energy greater than that of sigma 2pz. Then only sigma star 2s electron will be knocked out, isn't it? So which electron we will knock out generally? Generally an electron which is having higher energy, that electron only will be knocked out first. So here as per experimental result, we have to remove electron from CO from anti-bonding molecular orbital. So anti-bonding molecular orbital means only possibility sigma star 2s. Therefore, where sigma star 2s should be there? Sigma star 2s should be at this place. Therefore, what is the electronic configuration of CO? So what is the electronic configuration of CO? That we will see sigma 1s2, then sigma star 1s2, then sigma 2s2, sigma star 2s2. Keep it at last. Keep it at last. Okay. Therefore, pi 2px2 equal to pi 2py2, pi 2py2, then sigma 2pz2, then sigma star 2s2, sigma star 2s2. Like this, we have to write for CO. Okay, so for CO, how to write electronic configuration, you got an idea. Now we will write for CO plus. Now CO plus in the sense sigma 1s2, sigma star 1s2, sigma 2s2, pi 2px, pi 2px2, pi 2py2, pi 2py2, then sigma 2pz2, then sigma star 2s1. Now we will see the bond order. We will see for both. For CO, what is the bond order in the sense 3? For CO plus, what is the bond order in the sense 3.5? Because we have removed electron from antibonding. Therefore, bond order is raised by 0.5. If you remove electron from antibonding, bond order will be raised. If you remove electron from bonding, then and bonding molecular orbital, then bond order will be decreased. Now say bond order of CO plus is high. Therefore, bond length of CO plus is less. It is the experimental fact. Therefore, based on experimental fact, molecular orbital electronic configuration is explained. Okay. Therefore, this expectation is wrong. As per experiment only, we have to write. Therefore, in this electronic configuration, in CO electronic configuration, the think under exceptional case. Okay, so CO electronic configuration means exceptional case, like this you remember it. Okay, so then we will go for Cn minus. We will go for Cn minus. Cn minus is called cyanide. Here we will see the molecular orbital energy order. We will see first sigma 1s comes, then sigma star 1s, then sigma 2s, then sigma star 2s. Next, what will come? Okay, here what is there means carbon is there, nitrogen is there. Therefore, we need not say where we need not think about sigma 2pz. The up to nitrogen, what is the order? That order we can take. That's all. Okay. Therefore, pi 2px, pi 2px, pi 2py, then what will come means sigma 2pz will come. Then sigma 2pz. Next, what means pi star 2px equal to pi star 2py. Okay, then fill the electrons. Carbon 6, nitrogen 7, minus means additionally 1 electron, therefore totally 14 electrons. Therefore totally how many electrons means 14 electrons. Okay, therefore year 2, year 4, year 6, year 8, 10, 12, 14. Okay, so 14 electrons we have filled. 14 electrons we have filled as like nitrogen in the sense what is the bond order? Bond order is equal to 3. Bond order is 3, we can say. Okay, next we will take the molecule called HF molecule we will take. Now For HF molecule, how the molecular orbital configuration will be there, that we will see. Now we will take here fluorine atomic orbitals. We will take fluorine 1s, fluorine 2s. Here we will write 2px, 2px, 2py, 2pz. Okay, 2pz we have written. Now we will write the electrons. We will write here. So 1s contains 2, 2s2, 2px2, 2py2, 2pz1. It is the electronic configuration of each one in the sense fluorine. Next we will take a hydrogen atom. We will take, for hydrogen atom electronic configuration is what means 1s1. Now hydrogen 1s1 is near to 2pz of fluorine. Therefore 2pz of fluorine and hydrogen 1s undergoing linear combination. Therefore we will get what in the sense sigma sp and sigma star sp. Okay, sigma sp and sigma star sp, we will get it. Okay, now this 1s is having one electron, 2pz is having one electron, so totally two electrons. That two electrons goes to sigma sp. That two electrons is going to sigma sp, we can say. So what is the electronic configuration of HF? What is the electronic configuration of HF? We will see. For HF, what is the electronic configuration means this 1s2, then this 2s2 will write, this 2s2 will write, this sigma sp will write, sigma sp we are writing, then this 2px and 2py will write, 2px2, 2py2, then this sigma star sp, sigma star sp is having zero configuration. Okay, this 1s2 is called K shell, then 2s2 sigma sp2, then this 2px2, 2py2. Okay, it is a configuration of what in the sense HF molecule. So HF molecule electronic configuration we have given. Next we will see about HCl molecule. For HCl molecule, what is the electronic configuration, that we will see. HCl molecule, first we will write about Cl. For chlorine atom, we will see the electronic configuration. Chlorine atom 1s2, then 2s2, here 2p6, 2p6, here 3s2, then here 3p5, 3p5. So 3px2, 3py2, 3pz1, 3pz1. Okay, it is chlorine. Now we will see hydrogen. Hydrogen atom 1s orbital, hydrogen atom 1s orbital energy is nearly equal to 3pz orbital energy of chlorine. Okay, so here listen here, here hydrogen 1s1 energy is nearly equal to 3pz energy of chlorine. Okay, therefore which will go for overlapping in the sense 1s of hydrogen and 3pz of chlorine is going for a linear combination and gives sigma sp and sigma star sp. Now this 1s is having one electron, 3pz is having one electron. Those two electrons is going to sigma sp and sigma star sp is having zero electrons. So what is the configuration of HCl in the sense this 1s2, 2s2, 2p6, 3s2 will write. Okay, so 1s2, 2s2, 3, 2p6, 3s2. Then we will write the sigma sp we will write. We will write about the sigma sp we will write, then 3px, 3px, 3py, 3py, and the sigma star sp is not having any electrons, zero electrons is there. Now this 1s is called K shell, 2s to 2p6 is called L shell, then we will write 3s2 sigma sp2, then 3px2, 3py2 we will write. It is the electronic configuration of what in the sense HCl molecule. Okay, so HCl molecule electronic configuration we have given. Next we will go for a next topic called back bonding. So far we have discussed molecular orbital theory, that is completed. Now we will go for which one in the sense back bonding we will take. Now we are going for back bonding. Okay, so in the back bonding, what we'll discuss in the sense, we'll take the molecule called what in the sense boron trifluoride we'll take. We are taking boron trifluoride. Boron trifluoride in the sense central atom is boron, surrounding atoms is fluorine atoms. Okay. Boron comes under group number 3A. 3A in the sense this valence shell is having 3 electrons. Boron comes under group number 3A. This valence shell is having 3 electrons. Fluorine comes under group number 7A. Therefore, this valence shell is having 7 electrons. 7 electrons we have written. Now bonding takes place like this. Bonding takes place like this. In the boron electronic configuration, if you see helium 2s2 2p1, 2s2 2p1. This is 2s and 2p. Okay, we will write like this. 2s and 2p we have written like this. In the boron, 3 bonds are there. Therefore, it will go for sp2 hybridization. Therefore, sp2 hybridization. So one s orbital and 2 p orbitals undergo intermixing and gives what in the sense sp2 hybridization. So sp2 hybridization we have written. This 2p orbital is vacant. That 2p orbital will write. Okay, this is a vacant 2p orbital. Will say this here valency shell contains 3 electrons. Those 3 electrons will give here. These 3 sp2 orbitals go for sigma bonding with 3 fluorine atoms. Now this boron is having one 2p orbital which is vacant. Okay, set. So boron in BF3, boron in BF3 as vacant 2p orbital, as vacant 2p orbital we can say. Now this BF3 is having what shape in the sense a trigonal planar. BF3 is having trigonal planar. That means all the 3 bonds, all the 4 atoms present in one plane. Now this boron in BF3 is having vacant 2p orbital which is perpendicular to molecular plane, which is perpendicular to molecular plane we can say, which is perpendicular to molecular plane we can say. Okay, that is perpendicular to molecular plane. Molecular plane means all the 4 atoms, one boron atom, 3 fluorine atoms, all the 4 atoms present in the plane of this screen. Okay, now this 2p orbital of boron is perpendicular to this boron, perpendicular to this plane, like this you can say. Then that this perpendicular to, we said no, that we will take. Now we are taking that one. So vacant orbital of boron, vacant 2p orbital of boron we said. Okay. Then next point we will take a lone pair of fluorine. Lone pair of fluorine is perpendicular to molecular plane, perpendicular to molecular plane, like this we will take. This fluorine is having 3 lone pairs. Out of 3 lone pairs, one lone pair is perpendicular to this molecular plane. That we will take. Okay, so lone pair is present in perpendicular to molecular plane. Lone pair present in which orbital? In the sense present in 2p orbital. Present in a 2p orbital we can say. Present in 2p orbital. Now this vacant 2p orbital, this lone pair 2p orbital, both undergo what overlap in the sense linear, that means a lateral overlap. These two undergo lateral overlap, we can say. Therefore, a vacant 2p orbital, vacant 2p orbital of boron, vacant 2p orbital of boron, and a lone pair of 2p orbital, lone pair of 2p orbital of fluorine are perpendicular to molecular plane, perpendicular to molecular plane, but they are parallel to each other, but they are parallel to each other, parallel to each other. Therefore between them what overlap possible in the sense therefore sideways overlap is possible. Sideways overlap, sideways overlap is possible. Sideways overlap in the sense lateral overlap is possible. Lateral overlap is possible. Lateral overlap in the sense resulting what bond? In the sense pi bond we can say. So here lateral overlap is possible, resulting what bond? In the sense pi bond. This bond is called back bonding we can say. This bond is called back bonding. So back bonding present in BF3. Why BF3 is going for back bonding? What is the necessity of back bonding for BF3? That we'll see. Now boron in BF3, boron in BF3 is having, boron in BF3 has 3 sigma bonds. 3 sigma bonds in the sense 6 electrons. 6 electrons in the sense electron deficient. Electron deficient as per which one? In the sense after truth. Therefore, it is a electron deficient molecule. In order to nullify electron deficiency, this boron is going for what? In the sense this dative bonding. Because of this dative bonding, electron deficiency of boron is reduced to some extent. Therefore, this boron in BF3 is going for back bonding in order to nullify the electron deficiency only. Okay, therefore, in BF3, back bonding is there. Why back bonding is there? In order to nullify the electron deficiency of boron, that we can say. Next we will take carbon monoxide. In carbon monoxide, is there any back bonding? Is there any back bonding? That we will see. Now we will take carbon, we will take, and oxygen will take. This carbon valency shell is containing 6 electrons. Carbon valency shell contains 4 electrons. Oxygen valency shell 6 electrons present. 6 electrons will write here. Now we will give bonding. This is called one sigma bond. This is called one pi bond. Next, what happens means this carbon is providing a one vacant orbital.